And then let me share my screen. All right, well, thank you both very much for coming. Today I want to introduce a rather bizarre definition. It's going to build off of the definition that we had last time on looking at abstract varieties. So let me kind of remind you where we were, and then we'll focus on the new stuff for the day. So first, just a couple of quick announcements, just the usual things. Wednesday's lecture is now on YouTube, so hopefully you won't have any trouble seeing the recording there. I'll have office hours at the usual times, 11 a.m. after class this morning, and then 4 p.m. in the afternoon. And then just a reminder about the homework assignments. Number 7 is due today, and number 8 will be due next Friday. So I'll probably post number 8 sometime this weekend. But if you need any more time to get the homework assignments done, no big deal. I'm really happy to be really flexible about whenever these need to be turned in. Okay, so a quick recap from Wednesday. There were really 2 key ideas. Let me fix the following notation. F will be a field, and R will be the polynomial ring and n variables over this field. So first, we used some equivalent statements to define the idea of an affine variety. So let's say that we have a Zariski closed subset. So we'll write this here as V. Remember that Zariski closed just means that it's the zero set, for some collection of polynomials. So you can think of this as maybe like an elliptic curve or a conic section. So I just have a collection of polynomials, and I want this to be the zero set for that. So the following 3 statements are equivalent. First, it says that I cannot write V as the union of 2 other sets, both of them being proper and both being closed. Right? So remember, proper just means that V1 and V2 do not equal to our set V. And if I write here closed, that just means that I want it to be the zero set of some other collection of polynomials. Right? So that's the first statement, that I cannot write V as the union of 2 proper closed subsets. Number 2, this set IV, right? Remember that this is the set of polynomials that vanish at all of the points of V, that is a prime ideal. And number 3, this quotient, so R here, remember, is the polynomial ring and n variables, and I is the ideal from above. So it says that this quotient here is an integral domain. So again, you can use either one of these statements. They're all going to be equivalent. But if either is true, then we will say that our set V is an affine variety. Right? So this really is just exactly the same definition that we've been using all along. But now we're just kind of generalizing things a little bit by keeping track of things like this prime ideal IV, and then this integral domain OV. In fact, OV is what we're going to call the affine coordinate ring of V. Right, so we're going to play around with V versus IV in just a moment. Right. Now remember that if we fix a prime ideal sitting inside of our polynomial ring, R, then we can talk about the zero set of this prime ideal. Right? So this here is what we mean by a non-empty Zariski closed subset. Right? So it's just going to be the zero set of something. And we realize that we can compute IV here now as the radical of I. Right? So I forgot to say earlier that I'm always assuming here for today that F is an algebraically closed field. So whenever you think of the field F, it is always going to be algebraically closed. This is just so that we can make some rather simple statements today. So again, our IV now is just the radical of this ideal I, but I is a prime ideal. So the radical is just I itself. So I really don't have to worry about what the radical of I is. And I can look at this quotient, R mod I. This is just the coordinate ring of V. So again, if you start with an ideal I, a prime ideal I can look at this Zariski closed subset V, which of course is just an affine variety. I have the prime ideal IV, which is just I, and then I have the coordinate ring, which is just R mod I. Right? That's now all starting from a prime ideal I. Then we realize that there is an injective map that says, pick a point P. Right? So this is pick any point sitting inside of this affine variety. Then I can associate that to a maximal ideal. Right? So this is the maximal ideal corresponding to the coordinate ring, OV. And if you will, we can put all of this together to say the following. Let me look at the following equivalence, right, to this bijection. This says if I start with the point in V, I can think of that now here as an element of the maximal ideals of the coordinate ring, but that is equivalent to looking at the maximal ideals of R that contain I. Right, so all three of these are the same. I can either say, again, it's the points inside of my affine variety, or it'll look like the maximal ideals in the coordinate ring, or it'll just be those maximal ideals in the polynomial ring that contain this ideal I. Right, so they're all one and the same. It doesn't matter which definition that you use. But I'm going to use this idea here to write down a slightly larger definition. Instead of looking at M spec, let's look at spec. Right, so spec of O is what we're defining as an abstract variety. This is for O being any integral domain. Now, in what we've written up above, really an affine variety should be M spec of a Dedekind domain. That's really what we're defining as an affine variety. It really looks like M spec of a Dedekind domain, of an integral domain, but we're going to define an abstract variety as just spec of an integral domain, right? So really, we're just going to abuse notation here, and we'll just always say that spec of O is an affine variety, right? The reality is that it's really an abstract variety, but we'll just call it an affine variety. So now this is one of these weird ideas starting with Grothendieck and now part of algebraic geometry, that if you start with any integral domain that you want, then spec of that integral domain is a variety. Right? That's what we're defining here as an affine variety. All right. So we want to try to figure out how does this match up with things that we've seen up to this point in class. So I want to kind of reach all the way back to the beginning of the course, and I want to lay out some of the examples that we've done so we can kind of see what's the general trend that we've done up to this point here. So let's try to recap a few ideas from previous lectures. So number one, remember that we talked about this idea of a projective curve, and we really just said that a projective curve means that here we're going to have maybe just one polynomial equation where we have a homogeneous polynomial of degree E. Right, so this is just kind of our naive definition of what a projective curve is. And once we had this, then of course we wanted to talk about what does it mean to be a non-singular curve. So one way that we said that was to look at the partial derivatives of this polynomial, and we wanted to make sure that not all three of them are simultaneously zero. That was our idea of non-singular. But in order to say not all three of them are simultaneously zero, I'm going to change things around a little bit and say that this matrix should have rank 1. So remember that here I have a vector. A vector is still an example of a matrix. And so rank 1 just means that this is not the 0 vector. Right, so again, we're just going to move things around a little bit and say that in this case, a non-singular projective curve means that this gradient, this vector here, has to have rank 1. And of course, this should be true for all points in our curve. So once we have that, then of course we can define the genus of our curve as just this number here. Right, so here I have e minus 1 times e minus 2 over 2. And then finally, we have the idea of the tangent line. So here I'm asking for what are the set of all points where the sum here equals 0. Right, so remember that this is how we kind of use to figure out rational points on things like conic sections and elliptic curves. Here we have a tangent line, and we kind of draw and then look at where that intersects our curve. Okay, all right, so this will be our tangent line. So from here, we start to take a look at what happens as our degree E has different values. So when E is equal to 1, this is what we define as a projective line. And we found that this is always non-singular. Right, so E is equal to 1, it's very easy, it's nice to understand. When E is equal to 2, then this is what we called a conic section. And really here what we're doing is we have this quadratic polynomial and we're going to set this equal to 0. Right, so this is where we talked about things like circles and ellipses and hyperbolas, and eventually we looked at the Pell's equation. So all of this falls into this case here when E is equal to 2, homogeneous polynomial of degree 2. So we found that this here is a non-singular curve precisely when this discriminant does not equal to 0. Right, so this is one of the homework assignments that we have. So this is what we mean by a conic section. Projective curve, homogeneous polynomial, has degree 2, and this curve is non-singular, which we translate into just saying that this discriminant here does not equal to 0. Right. Now, when E is equal to 3, we called such a non-singular projective curve an elliptic curve. So here we did a little bit of work. We proved first that we can always reduce our curve, excuse me, to the short Weierstrass form. So we can really write everything in terms of like y squared is equal to x cubed plus ax plus b. But the reality is we can write everything here in terms of this homogeneous cubic polynomial. We just reduced everything down to these two coefficients, capital A and capital B. And then we found that here we know that we have a non-singular curve precisely when this discriminant here does not equal to 0. Right, so elliptic curves are now the nice natural generalization of conic sections. Okay. Now, unfortunately, things got a little bit complicated when we went to degree 4. And we didn't do the full general case. We only kind of focused on a very specific case. Really, we focused on this y squared is equal to f of x, where f of x here is this polynomial of degree 4. So it's like elliptic curves, we had the polynomial of degree 3, but in this case now here we'll have a polynomial of degree 4. So we said that really we don't want to embed this thing into P2, we actually want to embed it into P3. Right? Part of the issue was we have a couple of problems at the point at infinity. So here, remember that we're going to have 2 points at infinity. Again, we're always assuming that our f here is algebraically closed, so we can take square root, so we're okay. So we know now that we have these 2 points at infinity, and we can write everything in terms of these 2 quadratic polynomials, write them as f1 and f2. Right, so on the most recent homework assignment, we said that this was an example of a quadratic intersection. It's just what happens when you have the intersection of 2 quadratic polynomials. That's what we typically call a quadratic intersection. Okay. So we actually proved a few things about this here. We said that the following statements are equivalent. Number 1, our degree 4 polynomial, f of x, has 4 distinct roots. That was equivalent to saying that this discriminant here, delta x, does not equal to 0. And remember that we can really associate this to some kind of an elliptic curve by looking at this capital A and capital B. So our y squared is equal to a quartic really is an elliptic curve, where here we have our capital A, capital B. But the most important thing is that this discriminant does not equal to 0 if and only if the following matrix has rank 2. So here you'll see we have our JP, which is very similar to the original definition for a non-singular curve. There we said that we had a matrix that should have rank 1. Now you'll see that we should have a matrix that should have rank 2. right? So the goal for today is to talk about why did I go from rank 1 to rank 2? What might be the more general way of doing all of this? Okay, so any questions on the recap that we've been doing so far? Okay. So here's a few questions that are going to motivate what we're trying to do today. So number one, we know that if we start with an integral domain O, then spec of O is an abstract variety. It's really what we're calling an affine variety. Right? Remember, really M spec is what we want, but we can just say more generally, look at spec of O. So what I want to know is, we've defined an affine variety, but what do we mean by a projective variety? Okay, so far, we haven't touched at all what that means. Number two, what do we actually mean by a projective curve? Right, in some sense, we even have to define what a curve is, but we don't even really know what a projective curve is. And number three, what does it mean for all of this to be non-singular? Right, so far, we've really only talked about varieties, but we definitely haven't talked about non-singular varieties. So that's the goal for the day, is to introduce what we mean by non-singular. Right? So let's try to maybe take a step back. Let's take a look at some of the examples that we have, and let's see, can we maybe come up with a good way of defining what do we mean by non-singular variety? So let's return to the case that we're familiar with. We'll assume that we have an ideal I here that is a prime ideal. Let's say maybe it's just generated by m polynomials, f1 through fm. That will be a prime ideal of our polynomial ring R. Remember that R here has n variables. And let's define, in the usual sense, an affine variety as just the zero set here, and here we have m polynomials and n unknowns. Right, so we're not going to do anything fancy here. We're just saying, just give me a collection of polynomials and a collection of variables, look at when it's equal to 0, and go from here. Okay. So intuitively, this is what we want to be able to say. X is a non-singular affine variety if we can define a tangent. Right, that should just be what we're trying to do. Non-singular should mean that we have a tangent everywhere. So now we have to ask the question, what do we mean by tangents? So let's try to do this here. We know that we have a collection of polynomials, f1 through fm. So why don't we try to define, like we might in multivariable calculus, the Jacobian at a point? Right, so by Jacobian here, what we're doing is if I take the polynomial f1, then let's take a look at the partial derivatives here. And then if I have my polynomial fm, then let's take a look at the partial derivatives here. Right, so I have my various rows here that all correspond to the partial derivatives with respect to x1, x2, through xn. Right, so this here should be an m by n matrix. Right. So now if we think about it, I have m equations and n variables. So I better have more variables than I do equations. So everything's set up so that m is less than or equal to n. Right, that's the first idea. M here should be less than or equal to n. So what I want is for the rank of this matrix to be as large as possible. So I want the rank of this matrix to be m for every point. Right, so I'm going to come back in a couple of slides and say a little bit more of why. But again, if I have here m polynomials, then for non-singular, what I really want to say is that the rank of this matrix should be m. Right, so you can kind of remember what the other examples, like when I said a projective curve that was only generated by one polynomial, so the rank of my matrix should be 1. When we had the quadratic intersection, remember like with the quartic polynomials, then there I had 2 polynomials, f1 and f2, so I wanted the rank there to be 2. So in general here, what I'd like is for the rank to be m. Right, so I'm going to come back and explain how that is all related to this idea of saying that I really want a tangent at every point. right? So I do want to come back and say in a bit more detail what's going on
Professor Goins,
here. Yeah,
for the quartic, what was the second polynomial that generated it? Was it
here, I'll come back. Remember, it was these two here. So the F1 was kind of where we had like x3 equals to x squared. And then
uh-huh.
2 was when we kind of, whenever we saw an x squared, we just replaced that with an x3. So it kind of went from y squared is equal to a degree 4 polynomial to y squared is equal to a degree 2 polynomial.
Oh, I see.
Right. Yeah, so
Okay,
that was
all
just a
right.
trick that we did to kind of make sure everything was non-singular. That was kind of the
I
idea.
I understand. All right.
Mhm. Okay. All right. Okay, so let's try to think a little bit more. What are we doing here? Now, remember that growth and decay has this philosophy that instead of looking at the variety x, you look at the integral domain O. So this is the whole philosophy that I've been doing. Remember, also I started by saying that if we have a variety V, we can look at spec of the coordinate ring OV. So there's a way I can relate V with M spec of OV. So we want to try to relate these two. Whenever I see a variety X, I'm going to try to replace that with the ring O. So here's some motivation. So we can kind of think, what are we going to do here? Remember that X is the collection of points P so that f of P is equal to 0. Right? That was the idea. So I remember that I want X to be like the 0 set of this ideal I. So it's the set of all points where the polynomials are equal to 0 for all the polynomials. So let me actually try to do this. Let's say that our point P is in terms of A1, A2 through AN, and let me look at a Taylor series expansion. Right, so we're just going to take a polynomial and we can now evaluate at P. I can look here at, say, the first derivatives. So I have this here. I can then take a look at the second derivatives. So I have this here, and so on and so on. So if you haven't seen this before, this is like a Taylor series expansion, but now I have multiple variables. Right, so again, it's the Taylor series expansion, but it's multiple variables. So we can just do this whole thing of like the first derivative, second derivative, so on and so forth. What I really want to call your attention to is these polynomials here, x minus a1, that should actually be xk minus ak. And then here you'll see I have an xk minus ak and then an xj minus aj. Sorry, there's a couple of different typos here I need to go back and fix up. But you'll see here that I have maybe just one of these. Over here, I'll have two of them. And as I increase them, I'll have three and I'll have four and so on and so on and so forth. So I have a lot more here. So let's go back to our maximal ideal M sub P. So remember that we're working over an algebraically closed field. So every maximal ideal of the polynomial ring is in this form here for some point P. It's part of the reason why we prove that. So we know a whole lot about what the maximal ideals look like. Well, the maximal ideal is generated by these, right? These x1 minus a1. So if I work modulo fp, then really this just means that I kind of think of this as these two roughly are equal. So like this here should kind of be equal to f of p. Right? That's the rough idea. So if I were to kind of look at maybe, in a sense, almost adding a point, then I just get back f of p. Again, this is just this idea that these here should be equal. But if I work modulo mp squared, that will be these terms here. Right? mp squared just means literally you take the products of things from your maximal ideal. So if I work modulo the square, then now I see I actually get back a few more terms. Right? So again, remember that intuitively, when I work mod MP, what I really am doing is I'm evaluating at P. So whenever you really see like the x's here, it just says like plug in what happens at p. That's just kind of the intuition. However, when you work modulo the square, you're not just evaluating at p, roughly speaking, you're kind of looking at the first derivative, right? That's very roughly speaking what's going on here. So let me kind of recap in the following way. If I were to work with f mod the maximal ideal, that's like the same thing as looking at evaluate that at p. However, if I were to work with, say, f mod the square of a maximal ideal, very roughly speaking, that's like computing the derivative.
I have a question. It's like I kind of understand why f mod mp is the kind of like computing fp, but why like f mod mp square the same as computing the gradient?
Because what's happening here is this. Let me look at just this part here. Right. Remember that everything else that's here, this all goes to 0. Right, because we're working mod mp squared. Right, mp squared means I literally take the product of elements from mp. And this here, this xk minus ak, xj minus aj, that is a product of things from mp. So this here is an element of mp squared, which means that when I quotient by it, then I might as well just set this equal to 0.
Okay, yeah.
Right, so really what I'm saying is add the polynomial plus fp plus the linear part. And that's exactly what's here. Right, add the polynomial plus fp plus some linear part.
Thank you. Yeah, I think
Okay. All right. Yeah. Good. Yeah. Thanks for that question, because this is kind of a crucial idea here. We really shouldn't go any further unless this here really makes sense. Right. So I do want to emphasize that this is really one of these weird philosophical concepts. That remember that we're trying to look at the ring O. So what this says is, not only do I think of the elements f as functions on x, but quite literally I can evaluate those functions according to the maximal ideal, and I can even take derivatives of those functions by looking at this mod, the square of the maximal ideal. Right, it's a really weird concept. So again, if you work modulo the maximal ideal, now you're evaluating the functions. If you work modulo the square of the maximal ideals, now it's sort of like you're taking the derivative of the function. Right, that's kind of the philosophy here that Grothendieck outlined. Okay, so I'm going to try to put all of this together here on the next slide to kind of explain what's what. So what we actually want to do is work with this quotient. So MP is an ideal, it's a maximal ideal. MP squared is another ideal. It's not maximal, but it's just some other ideal. So I can talk about the quotient here, which is just going to be some subring. Right? So here's the big proposition. I'm going to assume, just for the sake of stating things simply, that n equals m plus 1. So here what I'm saying is, remember that n is the number of variables, m is the number of equations, it's the number of polynomials that will give us equations. So I'm assuming that I have one more variable than I do equations. Right, so if you really think about it, these are all of the examples that we've done to this point in this class. Right, even when we had our quartic polynomial, our quadratic intersection, there we had 2 equations, but really we had 3 variables. Right, so almost like, x1, x2, x3. So we're still in the same case here, n equals m plus 1. So the statement is that the following 5 are equivalent. Right. Now, I will say that some of this is going to build upon your knowledge of discrete valuation rings. If you don't know what those are, I would say don't really worry, because we're not really going to use them here. But I wanted to emphasize a lot of these statements because we're going to use this crucially in the next lesson. So first, we have that x is non-singular at a point P, right? And I'll go over on the next slide, what do I mean by non-singular? But remember, for the moment, this is something about a certain matrix has rank M. Second equivalent statement is that this subring is actually a vector space. And this vector space is one-dimensional. Right? So this is a weird concept. That here I have a vector space that's one-dimensional. Right? For those that know about discrete valuation rings, then I'll say it in the following way. OP, which is the localization at this maximal ideal, is a DVR. That's equivalent to saying that this maximal ideal, this is a maximal ideal sitting inside of the localization. This is a principal ideal domain. So actually this here is a principal ideal, so it's generated by one element. And this is equivalent to saying that the localization is integrally closed. So again, the last three here, we're not really going to focus on in this class. This is just saying that if you happen to know this, then here are the equivalent statements. This really is going to take us too far afield from where I want to go. So I'm not going to focus on these latter three statements. I do want to focus very crucially on the first two statements here. And we'll come back and I'll explain more of what I mean by this. So this here is actually a very big statement in commutative algebra. There's a very famous book by two commutative algebraists, Sir Michael Atiyah and McDonald. The book's called Commutative Algebra. It's kind of a very standard textbook in commutative algebra. It has proofs of basically everything that you'll ever need to know in commutative algebra. They only state all of this within a couple of pages, but it's kind of misleading because actually most of the book is kind of set up to prove all of these statements together. So if any of you have an interest in going into this field of commutative algebra, it's guaranteed that everyone will tell you that you have to read this book at one point or another. Right, so I do have the proofs of all of these statements in the lecture notes, but today I'm only going to talk about the first two statements here, 1 and 2. When n equals n plus 1, I'll just emphasize this again, I'm saying that the number of variables is one more than the number of equations. So there is a generalization of this statement here, but just for this class, I didn't want to focus on what's going to happen. So I only wanted to focus on the simple case for today, right? But certainly I could have stated this in much more generality and things wouldn't have been much more different. Okay, so I want to go over what's really going on here. What does this notation mean? What's actually happening? So let's just talk about why 1 and 2 are equivalent. Again, for the notes, I'll do the other ones, but I don't want to focus on the other ones for today because we're not going to need them. Let me start with the very general observation, and this actually was first worked out in a math paper by Oscar Zariski, I guess back in the 1930s, 1940s or so. And remember, Zariski is the same one that introduced the idea of the Zariski topology that we're using here in algebraic geometry. So Zariski observed the following. So I want to introduce some ideas from linear algebra now. That JP, that matrix, means that I can multiply a vector by the matrix to get back another vector. So quite literally, I'm using this JP as matrix multiplication. So if I were to stare at the kernel of that mapping, that's what we're calling here the tangent space. So you'll see here that I have these equations that correspond to looking here at these gradients. Right, so again, quite literally the tangent space, remember that we started earlier by looking at things like the tangent line? Well, now this is our complete generalization of that. So the tangent space here is quite literally the kernel of multiplication by this matrix. So this is where now the tangent space comes from. So I can use linear algebra to now look at the rank nullity theorem. So because the TP here is literally the null space, it's the kernel of this mapping, then I know that the rank of my matrix, the Jacobian matrix, plus the dimension here of the tangent space has to be n, has to be the number of variables. So if I just work backwards, the rank is equal to M if and only if this tangent space is actually a line. It's one-dimensional. Right, so again, what we've actually done here is we've related everything way back to the whole thing of these projective curves. So our tangent space, this weird collection of n variables and m equations, this here is a line. It is a one-dimensional vector space if and only if the rank of our Jacobian matrix is M. So in order to know that the rank here is M, I need to figure out, can I compute this dimension of the tangent space in a different way? Right, so Zariski was one who realized that actually you can relate all of this back to just this one-dimensional space by just looking here at this multiplication by this matrix. Right, but again, what we're going to try to do here is compute this here, this dimension, in a totally different way. So Zariski introduced the following concept. He said, let's take a look at the following pairing. So you want to think of this as like the inner product or the dot product if you're dealing with vector spaces. Take a vector here in the tangent space. So we'll write this here as x1 through xn. Now take a polynomial here in this quotient. And remember that by polynomial, if it's contained in MP, then that means that when I evaluate that polynomial at P, I get back 0. Right, so that's what the MP means. Evaluate that at P and I get back 0. And if I work mod MP squared, that roughly means I'm taking the derivative. So if I have a function, I literally am going to take the dot product of these two. Here I have a vector in my tangent space. Over here now I have the derivative, which roughly speaking is like m mod m squared. And so let's just write that out here. So this is literally the dot product. Right, so just taking the dot product of the gradient with this vector. So this here is what's called a perfect pairing. It's bilinear and it's non-degenerate. So what I mean by all of that is, number one, this TP here is a vector space. So I can talk about adding two vectors over here. And of course, the dot product means that if I have the sum of two vectors, then I have now the sum of two dot products. So it's bilinear in that sense. Similarly, over here, remember that this is a vector space as well. So I can talk about polynomials here where I can add them together. So if I have the sum of two polynomials f, well, the gradient means that if I take the gradient of a sum is the sum of the gradients, right? Just the sum of the derivatives. So if I have the sum of vectors x or the sum of polynomials f, then I would get back a sum of dot products over here. So that's what I mean by bilinear. Non-degenerate means something to the effect of, if this here is 0 for all vectors x, then f has to be 0. Or if this here is 0 for all polynomials f, then my vector x has to be 0. Right? So I'm not going to worry about the details here, but that's just what we mean by a perfect pairing. So bilinear and non-degenerate. I'm introducing all of this to say that actually the dimensions of these two are the same. Right? That's the important thing. So the dimension of the tangent space is 1, if and only if the dimension of this weird quotient over here is 1. But that was exactly what I meant by saying that 1 and 2 are equivalent. All right, so again, to recap, x is non-singular, means that the Jacobian here has rank m, which means that this tangent space here has dimension 1, which now means that this vector space here has dimension 1. Right, so that's what 1 and 2 equivalent means. The last thing I'll say here on the slide is TP here is what we're calling the tangent space at P. So because of this pairing here, this weird m mod m squared is what we're going to call the cotangent space at P. And again, if you want to know how they're related, it's exactly because of this pairing sitting over here. right? So it's almost like the tangent space is the dual to the cotangent space, right? There's a way that I have this pairing that relates the two of them. So this was all due to Oscar Zariski. So he's the one that kind of observed, really the tangent space is not what you want, it's actually the cotangent space. Okay, right. So I'm not going to worry about the rest of the proof here. All of the rest of the details are sitting in the lecture notes. The caveat that I'll give you is if you want to see the other ones, the other 3 through 5, you have to know a lot about discrete valuation rings. And if you don't, I would say don't worry about it because we're not going to use any of that here for this class. Where I want to end for the last couple of minutes is going back to elliptic curves. And I want to say, what is this cotangent space? Right, so how do I really think of this cotangent space here? So remember that the statements are as follows. My cubic curve is non-singular if and only if this discriminant is non-zero. It's non-singular, according to the previous proposition, if and only if this vector space here is generated by exactly one element, right? Namely that it's one dimensional. Right, so that's what I want to remember. Non-singular means this cotangent space is generated by exactly one element. So let's maybe just try to run through a couple of examples here. So let's start with this curve, which of course we know is an elliptic curve because the discriminant here is 16, it's non-zero. Let's relate that to the following polynomial and the following point. So if I look at the gradient, there's only one polynomial. This gradient has rank 1, right? It's non-zero derivative. I want the rank to equal to the number of polynomials. In this case, one polynomial, rank 1, so it better be non-singular. Now let's take a look at the maximal ideals to see how this all works. So here, my maximal ideal, I know is generated by just x and y. It's really going to look like x1 minus a1, x2 minus a2, but in this case, my point is 0, 0, so my a1 and a2 are just 0. So that's why it really is just generated by these two here, x and y. So remember that if I evaluate everything in here at 0, I should get back 0. If I evaluate x at the point 0, 0, I get back 0. I evaluate y at the point 0, 0, I get back 0. So that's what MP means. Everything that I evaluate at this point P should be 0. Now, if I compute the square of this ideal, then quite literally it's generated by pairwise products of the generators from MP. So it's generated by x squared, by xy, by y squared. All right, so my MP squared for the moment looks like, excuse me, it's generated by 3 elements. However, let's take a look at the variable x. And I'm going to write down this identity. X I can write as something times x squared plus something times y squared. So actually my x sits inside of MP squared. Right? So again, if I take a look at my variables x and y, really my polynomials x and y, I notice that actually x itself has to lie in MP squared. So actually this quotient here, it's not generated by 2 variables, by 2 polynomials. It's not generated by x and y. It's actually only generated by 1. It's only generated by y. Right. So again, this vector space, this cotangent space, MP mod MP squared, is not generated by 2 polynomials. It's only generated by 1. But of course, that's what we want. It wanted to say that it's a one-dimensional vector space. It's generated by just one thing. Okay. All right. I think for the sake of time, I'm not going to do the second example. The second one was just supposed to say that if things are singular, then actually my MP mod MP squared is a 2-dimensional vector space. Everything is totally screwed up. Right. But I think I'll just worry about that later, maybe if anyone has questions for office hours. So do you have any questions then on anything that we've talked about here today? Right. Okay, well, let's maybe call it a day then. So on Monday, what I want to do is say a little bit more about what is the definition of a non-singular variety. So far, I've only talked about what does it mean to be non-singular at a point, but then on Monday, what I want to do is completely generalize all of this so we can talk about an abstract non-singular variety. Okay. All right, well, everyone try to have a good weekend, and hopefully I'll see you on Monday then.
Have a good weekend.
Thanks, Professor Goins.
All right, thanks a lot. All right, see you later.
Have a good weekend. See ya.
All right, thanks.